Howdy. Today we're doing chapter 4. We're starting our concepts of uh, chemical reactions, chemical equations. And one of the keys to this that gets lost to a lot of new students is everything relies on Dalton's atomic theory. And so you want to keep in mind that you cannot turn one atom of one element into an atom of a different element. You can't gain or lose atoms. You can't split atoms. And so everything's going to be simple whole number ratios, no decimals, always whole numbers. And so let's start by getting an idea of a chemical equation, what the parts are to it, what it's trying to tell us. So let's start with a nice easy one. CH4 G plus 2O2 G CO2 G plus 2H2O L. Completely out of it. Alright. So nice and sloppy. Let's rewrite it. So, to get my first thing, you'll notice this G down here. That's new. That's called a state of matter. Oxygen gas here, you notice it has a G as well, goes to CO2 G plus 2H2O L. Alright, so first off, we have two sides to this. We have the reactants and the products. Every chemical equation, every chemical reaction then has reactants products. The problem is that so much of our modern technology is relying on copy-paste that students tend to think the reactants are always on the left. It's actually much easier than that. The arrow points to the products. So if I run out of room over here, A plus B, I can make it go down to C plus D. And so the products would be C and D. We could wrap it around to the other side. So it's really just a matter of following the arrow. The other things we have here, we've got our subscripts that are for our part of our chemical formulas. We've got a new set of numbers here, and that's at the beginning, and these are coefficients. So these coefficients will tell us how many of these we have. So this particular equation actually has 4 coefficients. And so there's going to be one before the first thing. So there's actually one before the first thing, one after the arrow, and one after each plus. And so if there's not a coefficient shown, it's understood to be a 1. So I can go ahead and add these 1s back in. Alright. What this is saying is that if I take one molecule of CH4 and react it with 2 molecules of O2, it will produce or yield or make, so the arrow can be produce, yield, or make 2 molecules of water. Okay. If I were to draw it out with the Lewis structures, we could draw it out real fast. So 1 molecule of CH4, 2 molecules of oxygen gas, 1 molecule of carbon dioxide, and 2 molecules of water. Now you can also get the mole-to-mole relationships. So this is also saying 1 mole of CH4 reacts with 2 moles of O2, plus 1 mole of CO2 plus 2 moles of H2O. What you cannot do is grams. You cannot read those coefficients to give you the gram relationships. Only mole to mole or atom to atom, molecule to molecule. Never grams. You'll notice I also used G and S and lowercase l and AQ. These are called the states of matter. States of matter. Easy enough. G is for gas, S is for solid. That one's going to be key. Later we'll deal with a lot of confusion when we get to solubility. If it's solid, it's not soluble. L would be a liquid. Aqueous is dissolved in water. Dissolved in water. Which, if it's soluble in water, it will be dissolved in water. That simple. Alright? So, when we read these, we always want to keep in mind that there's a conservation of mass. The total atoms on the left-hand side will be equal to the total atoms on the right-hand side. If we have the same number of each atom, for each element on each side of the reactants and the product, then we would say that equation is balanced. And balancing an equation can be a little overwhelming at first. So trying to balance an equation, I've listed out a bunch of steps in it, but it's really going to become something that you want to practice and get a feel for. So let's get an example here. C3H8 plus O2 goes to CO2 plus H2O. Now, to balance this, I like to make a list of each element on either side. I'm going to make a scoreboard, but what I'm really going to be changing are the coefficients. So let's go ahead and add an underline for each coefficient. There's one before the first, one after the arrow, one after each plus. So this equation has 4 coefficients. We are not allowed to change the subscripts because that would change the identity of that compound. And so if I, for instance, change this to a 2 instead of a 1, it stops being water and becomes hydrogen peroxide. So the math that I will do here, I have carbon, hydrogen, and oxygen, is really just going to be coefficient times subscript, and that'll be equal to my total. Now, if the element is found in more than one places, for instance, the oxygen on this side, then I'll add those up. Carbon, hydrogen, oxygen. So for this side, I have 1 times 3, 3 carbons. 1 times 8, 1 times 8 is 8 hydrogens. 1 times 2 to get my 2 oxygens. The other side's a little more complicated. 1, 2, and the math for the oxygen is actually this 1 times 2 plus this 1 times this 1. So I'm going to go ahead and add in my understood ones just while I'm getting used to this. Add those subscript understood ones in. It really helps. So this will be 3 oxygens. My goal is to simply change the subscripts, and I want to end up with the smallest whole number ratio that has these numbers the same on both sides. Whole numbers, but you can use a fraction temporary purposes to find the ratio. It's all about ratios. So I want to change either this subscript so that when I multiply it by 3, I will get 1, or I want to change this subscript in front of the carbon so when I multiply it by 1, I get 3. Because I want to keep whole numbers, I'm going to go ahead and change this one to a 3. 3 times 1 makes this 3. You'll also notice that changed my oxygen. So now the math for the oxygen is 3 times 2 plus 1 times 1. My advice on the oxygen, don't try to adjust this number, recount them. So I now have 7. A lot of the times people forget they already had 1, and so they'll try and add 6 to this, but we really already had 2 here. So do the math again. It's a lot easier. So carbons are fixed, hydrogens are not fixed, oxygens are not fixed. So here's something that seems to help me out a lot, is I want to avoid changing something and coming back and changing it again later. And a great place to end is going to be stuff like this. If I can get elements that are by themselves, they are called free elements. And so, this case, oxygen is a free element, and I want to save it for last. I also want to save any weird elements. In other words, things that are weird are things that are not carbon, hydrogen, nitrogen, or oxygen. We use those all the time. Anything else is weird. I like to start with the weird ones, just because they stand out. I also do the same for parentheses. So, free elements want to be last. So let's go ahead and do hydrogen next. I'll come over here, some number times 2, and I want it to be equal to 8. Or I could do some number times 8 and set it equal to 2. Now that's going to give me a fraction, so we want some number here times 2. We'll make that a 4. 4 times 2 gives me my 8 for my hydrogen. That also changed the oxygen. So now we have 3 times 2 plus 4 times 1. You'll notice it was this coefficient that got changed. So 6 plus 4 is 10 oxygens. Now I'm going to come over here and I can change this oxygen coefficient without changing anything else. If I'd done the hydrogen last, I might have come over here and tried to change it, and it would have affected the carbon. So here I can do some number times 2, and I'll set it equal to the other side, which is 10. So x comes out to be 5. I'll put a 5 here. And that will make my total 10. So I'm going to double check my ratio. I'm looking for simplest whole number ratio. So it's 1 to 5 to 3 to 4. Just looking at the coefficients. They're all whole numbers. They can all be reduced. And so I'll double check my math. And if everything's right, then we've got this one right. 1 times 3 is 3. 1 times 8 is 8. 5 times 2 is 10. You'll notice I like to do my work on the right hand side and my check on the left. 3 times 1 is 3. 4 times 2 is 8. 3 times 2 is 6. Plus 4 times 1 is 10. And we've got this one right. Put a little star there. This is what's great. I love this on a test. It's a powerful feeling. If you balance an equation and you've done it correctly, all your numbers will be whole number ratio. They won't be able to be reduced. You'll have the same on both sides. You can answer those questions. You know you've got it right. Oh man, I can't tell you how much I would love to have had that on any of my history tests for the teacher to walk by and say, hey, you got that one right. So let's do another one. KClO3. I'm going to go to KCl plus O2. Now this one's a little intimidating at first. I have K, I have Cl, I have O, Cl, and O. It only has coefficients in 3 places. 1, 1, 3, 1, 1, 2. Now this one is our first example of a trick we like to use. Least common multiple. Alright, so multiples of 2, 2, 4, 6, 8, multiples of 3, 3, 6, 9. I'm going to pick this 6. What I'm doing is this oxygen comes in packs of 3, so no matter what I change here, it's going to be some multiple of 3. This oxygen comes in packs of 2. So I've got Twinkies that come in packs of 2, and I got to feed 3 people. We need to buy 6 Twinkies. Alright? So I want 6 oxygens on this side. I'll put a 2 so that this becomes a 6. And over here, I'm going to put a 3 so that this becomes a 6. Now I need to go ahead and update my scoreboard here. I've got 2 potassiums and 2 chlorines. Here I still only have 1 and 1. A 2 in front would fix that. And this one's actually quite easy. Right? So least common multiple is our first big trick. Alright. Ooh, scarier. A lot of stuff going on. This one, you might be really intimidated by the oxygens because the math on it gets a little difficult. 1 times 2 times 3. It can be intimidating. But luckily, we spend so much time memorizing our polyatomic ions, we should recognize them. So when I make my list, because I have NO3 on both sides, I can go ahead and put my parentheses 1 over there, and I'm going to keep this NO3 together. So my list becomes much shorter. Now I've got the I. You'll notice I want to line that I up. It makes life a lot easier. If these two lists are not the same, you want to stop there. You've made some mistake either in predicting a product or in copying a problem. So coefficients, I've got 1 before the first, 1 after the arrow, 1 after each plus. 1 times 1 lead gives me 1 of those. 1 times 2 gives me 2 nitrates. You'll notice this 3 is part of the piece. I keep it as part of the piece. 1 potassium, 1 iodine. 1 times 1 for each of those. 1, 1, 1, 2. Easy enough. This actually then becomes quite easy. I'm going to put a 2 here to get my nitrates to be 2. That also changed my potassium to be 2. So I need to come fix that on this side, 2 potassiums. But that also affects the iodine. And now it's balanced. 1 to 2. 1 to 2. You'll notice they're all whole numbers. Okay. So what do we do if we need to use a fraction part way? That can be quite difficult. Let's do C4 H10 plus O2 goes to CO2 plus H2O. Carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. 1, 2, 3, 4, 10, 2. 4 coefficients. Okay. I'm going to start with the carbon, put a 4. I'm not going to change the oxygen lab because I'm going to have to change it as soon as I do this hydrogen. So let's go ahead and do the hydrogen first, as long as I remember to come back and do the oxygen. So now let's change my oxygen. 4 times 2 plus 5 times 1. 8 plus 5 is 13. Uh-oh. They're only in multiples of 2 over here. So it's either you can come through and multiply everything by 2 at this point, or you can do the algebra just like normal. And you'll notice when I do this, I keep it as a fraction. 13 halves. So that when I multiply 13 halves times 2, the 2's cancel out and I get my 13. So my ratio is 1 to 13 halves to 4 to 5. You are not allowed to end with a fraction, but we've got the ratio now. We just need to get rid of this fraction. To do that, we'll multiply all the coefficients by the same number. And I'm going to use the number that's on the bottom, just so it cancels out. So I'm going to multiply them each by 2. So 2 to 13 to 8 to 10. In other words, 2, 13, 8, 10. Come back and check my work. 8, 20. 13 times 2 is 26. 8 times 1 is 8. 10 times 2 is 20. 8 times 2 plus 10 times 1. 16 plus 10 is 26. We got that one right. Okay. So balancing these equations, there's really 3 tricks we'll be using. We'll be using least common multiple. You'll be using polyatomic ions. You really want to hold them together. What I highly recommend is you write the parentheses around things. And then you'll also be occasionally using fractions just temporarily to find the ratio. Always keep in mind you cannot end with a fraction in your final answer, but you can use it to find the ratio. Okay. So now we're ready then for the types of reactions. So after you have balanced them and done a lot of those, you want to learn, and at this point we've got to pretty much memorize the types of reactions. Switched a little bit bigger pen for this one. So there are several types of reactions. The first one is a combination or a synthesis reaction. In this reaction, you take the pieces and put them together. And you can recognize when this reaction is taking place, there'll only be one product. In other words, no plus on this side. We do not expect you to be able to predict the products in a synthesis reaction. You just don't have the chemistry yet. The other one is an analysis or decomposition reaction. It's analysis if we do it on purpose. Decomposition if it happens by itself. It's just the opposite. You take something that's complicated and break it to its pieces. And it might have 2 pieces, it might have 3. The key is it's only got one reactant. We're breaking something apart. You cannot predict these at this point, so that's good. We just need to be able to recognize them and to balance them. Second on our list, third I guess, single displacement. The lab book calls it single replacement. I've never seen any other place call it that. So A plus BC goes to AC plus B. Now this is one that can be a little complicated. It's definitely one we want you to be able to predict. And so you want to learn this pattern, but it's also got a couple extra details. First, the A by itself. Now they may move that BC, you might see BC plus A, but the thing by itself will have a zero charge. When it's with something, it'll have some kind of positive charge. We don't know what, but it'll be a positive. The C has a negative charge of some kind. Now the B, when it's with the C, it has a positive, and when it's out here, it'll be neutral. What this means is we've taken some electrons and transferred them from A to B. So this will be one that involves electrons being transferred. Okay. Double displacement we'll see a lot more of. Double displacement AB plus CD will go to AD plus CB. And we're swapping partners. A and C have positive charges, and B and D have negative charges. What's nice about this is whatever the charge A has on the left-hand side, it'll have the same charge on the right-hand side. Whatever charge B has, it'll have that same charge. All we did was swap partners. You'll notice A and C will never go together. They're both positive. Positive things repel. And so we will never ever see B and D or A and C. Only new combination is right here. Okay. Next we've got, just flip this over, combustion, and its formula is some fuel plus O2, and it will go to CO2 plus H2O. Now, normally we would also include plus waste, but everything that we do in class and in lab and on our tests will be completely combusted. It'll all go to CO2 plus water. But if you've ever gotten behind a school bus, you know, coming out of the tailpipe, it's not all CO2 and water. That's why it's a big black cloud, right? So, it doesn't all combust. But this is saying that when I take wood in my fireplace, it makes carbon dioxide. It also makes water. Now my carpet doesn't get wet because this water is hot enough it leaves as water vapor. Okay? So one other set of reactions we have, precipitation reactions, and this will be one or more solids formed. So a precipitation reaction forms one or more solids, and all the precipitation reactions we'll see will be double displacements. Not all double displacements are precipitation, but every precipitation that we see will be a subset of double displacements. We'll look at solubility rules and learn how to deal with those in predicting what solid will be formed. Okay. Now these archetypes are used to find and predict our reactions. So if I have a reaction and I want to figure out what reaction type it is, and then I can do that by matching the patterns. So here I have hydroxy group. I'm going to go ahead and put that as one thing. Here's an A and a B plus a C and a D. So I can already identify this is a double displacement. When I'm trying to predict the products AD plus CB, I'll use these archetypes. I'll use those to predict what these products are. So the A piece is K, the D piece will be Cl, the C piece is Na, and the B piece is OH. Now, the problem with this is I have new partners, and so they will need new subscripts. We will have to find these subscripts. And so when we're doing these, we'll have to finish out these products by finding their new subscripts. So let's get a list of those steps. 1, you figure out what reaction type it is. That includes drawing the archetype. 2, you find the product parts, just like we did up here. 3, you're going to use the charges to find the new subscripts. What that's going to mean then is when we're in part 2 and I'm bringing over these pieces, I'm not going to bring over any subscripts unless it's part of a polyatomic ion. So if it's part of the piece, it comes with the part. But if it's just the subscript, tell me how many I have of those, and we're going to use the charges. And so remember, that is subscript times charge plus subscript times charge equals the total charge. Alright. 4th step, we will go ahead and balance the equation once we have the new subscripts. And then the 5th step, we'll do solubilities once we know how to do that. So finishing out a reaction, not super difficult, but it can be a little bit overwhelming at first. We want to know what type of reaction this is. So the first step then, I'm going to look, this is polyatomic ion, A with B plus C, D. So I'm going to go ahead and predict it goes to AD plus CB. You must memorize the archetypes. The A piece is NH4. I'm bringing the 4 because it's part of the piece. The D piece is Cl. The C piece is K. The B piece is NO3. We bring that 3. The charges, ammonium has a +1 charge, Cl has a -1, potassium has a +1, nitrate has a -1. I crisscross, it's 1 to 1, and I've got 1 of each. That one's not too bad. This one's a little bit more complicated. Again, A, B plus C, D goes to AD plus CB. A piece is Cu, D piece is I, C piece is K, and the B piece is NO3. The 3 is part of the piece. Notice I did not bring the 2, just the 3 because it's part of the piece. Now the problem here is copper can have multiple different charges. But this is a double displacement. Whatever its charge is on the left, that's what the charge will be on the right. Let's find the charge on the left. 1 copper times X plus 2 nitrates. Each nitrate is a minus 1. Set that equal to the total charge. There's nothing up here, so it's 0. X minus 2 equals 0. X is 2. This copper is a plus 2. That means this copper is a plus 2 on the right hand side. Iodine is in group 17. It'll be a negative 1. Potassium's in group 1. It'll be a plus 1. Nitrate is always minus 1. How do we know that? Memorization. Now I can do my crisscross. So Cu I2 plus KNO3. Almost done. Now I need to balance it. I've got 2 iodines on this side. Let's get 2 iodines on that side. Okay, it gives me 2 potassiums, 2 iodines. Oops. 2 potassiums. Now I have 2 nitrates and 2 nitrates, 1 copper, 1 copper. You'll notice I didn't make the list out. Some people like to go 1 element at a time. That works fine. You can make the scoreboard. You can do 1 at a time. Whatever works for you. The math is still the same. Coefficient times subscript. Okay, so practice some of these out of the pre-lab. Practice them out of the book. Get to where you can balance the equations. Get to where you can predict the products and recognize the reaction types. We'll spend more time on these in the next video.